tonight we are looking at the idea of electrolytes as well as just acids and bases, what pH means, what concentrated means, what dilute means, and then strength of acids and bases. So the first thing is an electrolyte is a substance that when dissolved in water results in a solution that can conduct electricity. Conversely, a non-electrolyte is a substance that when dissolved in water results in a solution that does not conduct electricity. Typically electrolytes are ionic compounds. Get my pen going. So typically electrolytes are ionic compounds. And typically non-electrolytes would be covalent compounds. Here's some kind of pictures to represent it. If we dissolved, let's say, sugar, which is a covalent compound, it's made of carbons, hydrogens, and oxygens. And if this was sugar water, and we have a couple wires hanging in the water, this light bulb would not light up because sugar is a non-electrolyte. If we had something like this, maybe some vinegar. Okay, vinegar, we'll see in a little bit, is a weak electrolyte. It's a weak acid, and it would conduct electricity to a certain extent. Alright? And then lastly, if we had something that was a strong acid, or just put salt in water, table salt is an ionic compound. It's sodium chloride. It's made up of a metal and a non-metal. But salt water conducts electricity very well, and it would light up the light bulb completely. So anyways, electrolyte, non-electrolyte. Acids. Just a couple kind of characteristics of them. If you taste it, it tastes sour. A couple examples: vinegar, citrus fruits contain citric acid, stuff like oranges, grapefruit, lemons, limes, all have a sour taste. Second, with certain plant dyes or acid-based indicators, acids cause a color change. Possibly in general chemistry, if you used red cabbage juice, you saw how acids can change red cabbage juice. Otherwise, you've probably seen phenolphthalein or other acid-based indicators. They react with certain metals to produce hydrogen gas. It depends on the acid. Hydrochloric is a great example. If we react it with pretty much any of the alkali or alkaline earth metals, so we have hydrochloric acid, which is aqueous, or just it's in a solution. We put some solid magnesium in it. We get magnesium chloride as an aqueous solution, and we produce hydrogen gas. Okay, this is an example, or this is a equation or a reaction that you're going to have to memorize in January. We'll kind of start looking at equation writing. So the earlier you can memorize these, the better off you are. So again, if you can just think in your head, acids with metals typically produce hydrogen. Another reaction is acids with carbonates or bicarbonates. So just think of CO3 2- or HCO3 1-, produce carbon dioxide and water. Here's an example: hydrochloric acid plus calcium carbonate. This is limestone, which we have a whole lot of here in the state of Kansas. And actually, geologists typically carry around hydrochloric acid with them, just in a little vial. If they put some drops of hydrochloric acid on limestone, they will see bubbling. What is the bubbling? It is the carbon dioxide gas that's being produced. And as well as carbon dioxide, we're going to get some water. And we get calcium chloride just in a solution. And then lastly, aqueous acid solutions conduct electricity. If we have strong acids, which there's a number you have to memorize, they are strong electrolytes. And if it's not a strong acid, if it's a weak acid, it's going to be a weak electrolyte. Alright, so bases, a couple of characteristics of bases. They have a bitter taste. Okay, so acids are sour, bases are bitter. They feel slippery. Most soaps, if you look on the backs of them, they will have some sort of base in them. And so if you think of soap, slippery, and it has a base. And again, they cause color changes in plant dyes, or stuff like phenolphthalein. If you ever use red cabbage juice, you've seen that color change. And I think that does it for bases. Alright, so pH scale. What in the world does pH mean? pH stands for the power of hydrogen. So little p, this is just the H from the periodic table, but the power of hydrogen. The pH scale compares the number of hydrogen ions to other ions in a given sample. I'm going to use the hydrogen ions interchangeably with hydronium. And this might be a new term for some of you, but H3O+. And really, we don't have H pluses floating around when we have acids. We really have H pluses. And because most acids are in water, it's really this H plus attaches to an H2O to form what's called hydronium ion. And that's HYDRO. Hydronium. I don't know why I did a D there. Hydronium ion. Okay, so the pH scale compares the number of hydronium ions to other ions in a given sample. Samples with pH between 1 and 6 are considered acidic. Those with a pH of 7 are neutral, and those with a pH between 8 and 14 are considered basic. Okay, so low numbers are acidic, high numbers are basic. 7 in the middle is considered neutral. Here's some just pHs of common substances. The main thing that I want you to see is we usually talk about the pH scale, but there's another scale known as pOH. Alright? And when we talk about acids and bases in February, we'll go much more in depth. We're kind of just doing a broad overview of lots of different types of reactions in this unit. But notice when the pH is 14, pOH is 0. Notice when the pH is 10, pOH is 4. When pH is 7, pOH should be 7. It looks like our 7's over here for some reason. When the pH is 4, pOH is 10, and if the pH is 0, pOH is 14. So just to point out, pH plus pOH always equal 14. So when we're looking at hydronium ions or hydrogen ions, they occur in the absence of OH. Okay, but they're always kind of in, I think of a little seesaw, and we have H pluses floating around, we have OH minuses floating around, and if the seesaw is kind of pointing towards the H plus, we say a substance is acidic. If our seesaw is kind of weighted towards the OH, we say our substance is basic. Okay, but it's always on some sliding continuum between how many H pluses do we have in relation to OH minuses. Here's just another way to look at it. If our hydroniums are high, if our concentration in moles per liter is in the less than 10 to the negative 7th, so we're really looking at fairly dilute solutions, but if it's between 10 to the negative 7th and 10 to the negative 1st, it is acidic. And if it's less than 10 to the negative 7th, so it's really, really dilute, it would be considered basic. Okay? Alright, there's a couple ways we can define acids and bases. The first way is going to be Arrhenius definition. Alright, and an Arrhenius acid is a substance that produces H plus in water. So here's kind of a graphical representation. We have HCl, we have a water molecule. This HCl, when we put it in water, really it produces H plus, because we're saying that hydronium is synonymous with or equal to H plus. Okay, so Arrhenius acids are substances that produce H plus or hydronium in water. So when we add these things, this bond gets broken, the H goes with the H2O, and the Cl is just now floating by itself. Conversely, Arrhenius bases are substances that produce hydroxide in water. And again, there's this here. This is our hydroxide is the OH in pOH. Okay, so H is always referring to pH is always referring to hydrogen ions. pOH is always referring to hydroxide ions. But if we have ammonia and we put it in water, we form ammonium. Okay, so notice that one of our waters, this bond breaks, and this hydrogen attaches to the ammonia to form ammonium. And what's left, we have an OH minus, which is what makes ammonia basic. So again, the Arrhenius definition is that acids produce H plus and bases produce OH minus. Here's a hydronium. Kind of have the O in the middle. We have an H over here, H over here, H over here. We'll talk about geometries in a little bit, but there's kind of a lone electron pair up here. It's kind of a tetrahedral shape, or trigonal, or tetrahedral geometry, trigonal pyramidal shape. There's terminology you'll have to come back to you in, I don't know, a couple weeks, 3 weeks, when we start talking about shapes. Alright, the other definition, which is more standard now, is the Bronsted, and usually it's called the Bronsted-Lowry definition, in contradistinction to the Arrhenius definition. So the Bronsted acid is simply that a Bronsted acid is a proton donor. What is a proton? It is an H+. Okay? What is a Bronsted base? It is a proton acceptor. Alright, so again, we kind of have the same example. But notice, NH3, what is it doing? It is accepting a proton from water. So it makes this a base. What is water doing? It is donating a proton, so it makes water an acid. Alright, and that's going in the forward direction. If we go in the reverse direction, we have ammonium, and what does ammonium do? It donates a proton to OH-. So going this direction, this now becomes our acid. And our OH, what does it do? It accepts a hydrogen, it becomes our base. Alright, so because it's confusing to have two bases and two acids in the same formula, by definition, things on the left will always be assigned acid-base, but NH4 will be known as the conjugate acid. So, conjugate acid. And it's the conjugate acid of this base, where OH- is the conjugate base of the acid on the left. So hydroxide is the conjugate base of water. Ammonium is the conjugate acid of ammonia. Alright, this definition is a little bit better because not all bases produce hydroxide, which kind of eliminates the Arrhenius definition, but all bases do accept protons. So because of that, a Bronsted acid must contain at least one ionizable proton, or one proton that, when put in water, dissociates so that we make some H+. And when it makes H+, we're going to have something else, which we're just going to call A for acid, some negative ion, or some anion. Alright, strength versus concentration. Strong acids dissolve completely in water to produce hydrogen ions or hydronium ions and its anion. Strong bases dissolve completely in water to produce hydroxide and its cation. The main thing here is strong is completely dissolves. Strong bases completely dissolve. There are 5 strong acids that you need to know. I'm going to put them up here. Hydrochloric, hydrobromic, bromine is just below that, hydroiodic acid are 3 of them. The next one is nitric acid and sulfuric acid. If you remember, these are the 5 strongs. Everything else you can just think of as being a weak acid. Okay? These are the 5 strongs. You might add perchloric HClO3, but if you remember these 5, you should be pretty good. And if it's not these 5, it's going to be a weak acid. Strong bases are typically alkali and alkaline earth metals with hydroxide. So alkali and alkaline earth with hydroxide. So strength deals with, do they dissolve completely or do they not dissolve completely? And concentration deals with how many molecules of acid or base are actually in the sample. Here's a little table that might help you differentiate a little bit. But we can have a concentrated and strong acid. What that means is there are lots of acid molecules, okay, and this refers to concentration, added to the water, and almost every molecule donates its hydrogen, okay, or almost every molecule dissociates, or it breaks up, which would mean every molecule donates, would refer to strength. We can also have a dilute strong acid, which means there's only a few acid molecules, but almost all of those molecules, even though there's a few of them, dissociate and donate their hydrogen. We could have a concentrated acid that's weak. There's lots of acid molecules, but because it's a molecule that doesn't donate much of its hydrogen, even though there's lots of them, there's very few that donate their hydrogen, so it's still a weak acid. A good example of this is vinegar, which is known as acetic acid. And then dilute and weak. There's really only a few molecules. That refers to its diluteness, or its concentration. And it has a few molecules, and only a few of those donate their hydrogens. Again, refers to its weakness. So dissociation refers to strength, is it strong or weak, while numbers of particles refers to its concentration. Monoprotic. What's mono mean? It means one. Protic refers to proton. So monoprotic acids are those acids with one H. So something like hydrochloric acid. In this case, it's one of our strongs. So it's a strong electrolyte, it's a strong acid. If you have nitric, it is a single proton acid as well. It's another strong electrolyte or strong acid. And here is acetic acid, or vinegar. It's sometimes written like this. It can also be written like this. CH3COO. It can also be written like this. HC2H3O2. And those are the kind of the common other ways to write it. This is the organic way to write it. And what we'll find out over Christmas break is this is a carboxylic acid. Usually if we're not writing organic stuff, we usually write it like this way, where this looks like the acetate ion. Okay, but vinegar is a weak electrolyte because it's a weak acid. We can also talk about diprotic acids. Diprotic acids are acids with two protons. So a good example is sulfuric acid. And notice here it has two hydrogens that it can lose. When it loses its first hydrogen, it is a strong acid. Alright, so it's a strong electrolyte. If it was in water and we had a light bulb attached, it would light up brightly. If it loses its second hydrogen, however, this second one is known as a weak acid, or a weak electrolyte. Because it's hard to get this by itself, if we put sulfuric acid in any kind of water, we see the effects of this one, and this happens at a lesser degree, and again, we'll kind of look at that more in detail when we look at acids and bases second semester. And then triprotic acids, our best example is phosphoric acid, H3PO4, and it is weak every single time. But again, it has three hydrogens to lose, so there's kind of three equations we can write down as it goes to H2PO4, then it goes to HPO4, and finally to just phosphate ion. Identify each of the following as a Bronsted acid, base, or both. All right, so if we look at this first one, HI. Alright, so what can it do if we put it in water? Can it accept a hydrogen? No. Can it donate a hydrogen? Sure. So it can donate a hydrogen to water. This is happening in water. We might write H3O+, hydronium instead. But really we have H+, and I-. It donates a hydrogen, so it is an acid only. If we look at acetate ion, so we have CH3COO-. If we have that in the presence of water, what is going to happen? Because this is an anion, it has a negative charge, it wants to accept something that's positive. So we're actually going to make acetic acid. Alright, and in the process we also make hydronium. But according to Bronsted-Lowry, we just want to know about hydrogens. So hydronium is not important to us. But what did this do? It accepted a hydrogen, so it is a base, according to Bronsted-Lowry. And then lastly, C, we have H2PO4 -1. Well, just like we had in this example, because we have a negative ion, an anion, it can accept a hydrogen. So this can become H3PO4. And what did this H2PO4- do? It accepted a proton, which means it's basic. But what else did it do? Or what else could it do in the presence of water? Because it has other hydrogens that can lose, it could just as easily make hydronium and HPO4 -1. And in this instance, because it's donating a hydrogen, it is an acid. Alright, and just some terminology, this thing, H2PO4, is known as amphoteric. it's known as amphiprotic. Amphiprotic. Alright, so protic still has to do with proton, and ampho, or amphi, if you think of amphibians, where do they live? When they're born, they live in the water. When they're adults, they live on land. So they live both in land and water. So the prefix amphi or ampho means both. So it's both able to lose a hydrogen and it's able to accept a hydrogen. So something like this is known as amphiprotic because it can do both. It can act as an acid or a base. Right, the last equation that we're looking at tonight is known as a neutralization reaction. So we kind of looked at acids with certain metals produce hydrogen gas, acids with carbonates and bicarbonates produce carbon dioxide and water. If we mix an acid and a base, we always get salt in water. And salt here is not just NaCl, but salt is any ionic compound. So in chemistry, salts are ionic compounds. Unfortunately, this example has HCl, hydrochloric acid, plus sodium hydroxide, yields sodium chloride, which is table salt, and water. But any acid-base reaction, so if we had HBr plus potassium hydroxide, we would get potassium bromide, which is not table salt, but it is still a salt because it's ionic, plus water. Okay, so neutralization reactions, and that does it for the podcast tonight. Kind of real quick, just an introduction to acid-bases, electrolytes, and there'll be more reaction types as we go through this unit. Otherwise, have a great night, and we will see you tomorrow.